was 319. I'm on 320. 320. All right, let's continue reading on. Figure 318 illustrates some of the conditional move instructions available with x86-64. Each of these instructions has two operands, a source register or memory location S, and destination register R, as with the different set and jump instructions. The outcome of these instructions depends on the value of the condition codes. The source value is read from either memory or the source register, but is copied into the destination only if it is specified condition holds. The source and destination values can be 16, 32, 64-bit long. Single byte conditional moves are not supported. Unlike the unconditional instruction, where the operand length is exactly encoded in the instruction name, the assembler can infer the operand length of the conditional move instruction from the name of the destination register, and so the same instruction name can be used for all operand lengths. They say instruction name. I think mnemonic is the term that most people use. Unlike conditional jumps, the processor can execute conditional move instructions without having to predict the outcome of the test. The processor simply reads the source value, possibly from memory, checks the condition code, and then either updates the destination register or keeps it the same. Yeah, it's the same instruction regardless of like which path you take. I can see how that would avoid having to be predicted. It's like, we're just going to do the work, and that work is based on some other data, but as far as like keeping the pipeline filled, it's not like a branch where you have to go and like fetch instructions from a totally different place of memory and then put them in the pipeline. To understand how conditional operations can be implemented via conditional data transfers, consider the following general form of conditional expressions in assignment. Let's look at a table here before we do that. So these are all based on different conditions, so equal, not equal, negative, not negative. They'll all check the different flags. The conditional move instruction, these instructions copy the source value S into destination R when the move condition holds. Some instructions have synonyms, alternate names for the machine instruction, for the same machine instruction. Wonder if I'll need to reference this later. So there's the general, what did they say this was? The general form of condition expression in assignment is test expression, then expression, else expression. So basically like a ternary. The standard way to compile this expression using conditional control transfer would have the following form. If test expression go to false, then expression go to done, else expression. Okay. This code contains two sequences, one evaluating then expression and one evaluating else expression. A combination of conditional and unconditional jumps is used to ensure that just one of these sequences is evaluated. For the code based on the conditional move, both the then expression and else expression are evaluated, with the final value being chosen based on the evaluation test expression. This can be described by the following abstract code. So you got then, else, and test expression, and then if test, then we just sign. Yeah. V gets the then expression. VE is the else expression. Test is computed. And then we do the conditional move based on the test T of VE into V. The final statement in the sequence is implemented with the conditional move. Value VE is copied to V only if test condition T does not hold. Not all conditional expressions can be compiled into conditional moves. Most significantly, the abstract code we have shown evaluates both then expression and else expression regardless of the test outcome. If one of those two expressions could possibly generate an error condition or side effect, this could lead to invalid behavior. Such is the case for our earlier example. Indeed, we put the side effects into this example specifically to force GCC to implement this function using conditional transfers. As a second illustration, consider the following function, C function. So you got cRead, returns a long, takes in a long pointer xp, and returns xp, dereference, or 0. At first, it seems like a good candidate to compile using conditional move to set the result to 0 when the pointer is null, as shown in the following assembly code. But you can't dereference the xp. So xp is an RDI, it gets dereferenced immediately. Dereference, I mean, it's going to be a memory protection fault, segmentation violation. This implementation is valid, however, since the dereference of xp by the move q instruction, line 2, occurs even when the test fails, causing the null pointer dereference error. Instead, the code must be compiled using a branch code. Using conditional moves also does not always improve code efficiency. For example, if either the then expression or else expression evaluation requires a significant computation, then this effort is wasted when the corresponding condition does not hold. Compilers must take into account the relative performance of wasted computation versus the potential for performance penalty due to the branch misprediction. In truth, they do not really have enough information to make this decision reliably. For example, they do not know how well the branches will follow predictable patterns. Our experiments with GCC indicate that it only uses conditional moves when the two expressions can be computed very easily. For example, with single add instructions. In our experience, GCC uses conditional control transfers even in many cases where the cost of branch prediction would exceed even more complex computations. Overall, then, we see that conditional data transfer offer an alternative strategy to conditional control transfer for implementing conditional operations. They can only be used in restricted cases, but these cases are fairly common and provide a much better match to the operation of modern processors. Okay. So now we got two practice problems, and then we go into loops. Okay. In the following C function, we have the definition of an operand op, incomplete. So we got arithmetic short x returns a short, return x op 16. My compile GCC generates the following code. So we got short arithmetic x in RDI. They gave me everything up front here. Okay, so we got the addition of RDI with 15. And the op is 16. Our BX Oh, I forgot I left my drink in the freezer. I'm gonna go grab it. I always leave these in the freezer and then they explode on me, which is not fun. But my fridge doesn't cool them down far enough. Anyways, so X is RDI. So we add 15 to RDI and store it in RBX. And then we do a test quad word on RDI to set all of the flags. And we do it with itself. And then we do conditional move NS. NS is not signed. So it means it's either positive or 0. In which case we move RDI into RBX. And then we do a signed arithmetic, arithmetic shift. I think SARC is arithmetic shift. Yeah, it's shift arithmetic. Shift right arithmetic. Yeah. Okay, so we do a right shift 4. So we drop 4 bits. Jesus Christ. So we're adding 15 and then shifting right 4. So it's asking what is the operation. Oops. Annotate the code to explain how it works. Okay, well, grab the code here. That didn't work. That didn't work. Let's try that again. Okay, load effective quad word. This thing adds 15 to x plus 15. Sets flags for x. Sets flags based on, say based on x. And this thing is do a conditional move of x. So this would be if x is greater than or equal to 0, then RBX is equal to x. And then this is a shift right 4. So this is going to be x equals, can I do a divide equals here? Yeah, divide equals if you shift right 4, you're dividing by, so 1 would be by 2, 2 would be divided by 4, 8, 16, divided by 16. So this is going to be something about division by 16, because the source code, the original op was, or the original value is x16. So I don't actually know off the top of my head. I could think for a little bit here. I'm tempted to say division because division lines up with 16, but I don't know what this plus 15 is. Yeah, I don't know. And return is RAX. So why are they using RBX? The fuck? Let's go back to our table here. RBX is the callee saved register. It's not even being returned. This code is like fucked. I don't think they, I think they made a mistake. At the very least, it should be RAX, right? And not RBX if you're returning it. Because this thing just returns whatever RAX happened to have set before this was called. Sorry, that's the wrong operator. That's the modulus, not divide. Division. I mean, it's doing their division as the last operation. I don't know what the preamble here is for the load effective address quad word to add 15 to RBX. Maybe to make the division. If it's negative, it adds 15 basically. Maybe it's between the division operator in C, the semantics of that, and the assembly shift right. I'm not sure. Let's check the book though. So 320. This problem provides a chance to study the use of conditional moves. I got the operator right. Yeah, the operator is division. We see this example of dividing by power of 4 by right shifting. Before shifting k by k, we must add a bias, which is 2 to the power of k minus 1 is equal to 15 when the dividend is negative. Yeah, I forgot about the biasing when it's negative. Here's the annotated version of the assembly code. The program creates a temporary value. So here it says temp is equal to x plus 15. test x. If x is greater than or equal to 0, they use the value temp instead of rbx. And then the result is rbx divided by 16. Okay. The program creates a temporary value equal to x plus 15 in anticipation of x being negative and therefore requiring biasing. The C conditional move not signed instruction conditionally changes this number to x when x is greater than or equal to 0, and then it is shifted by 4 to generate x equals 16, or x divided by 16. Okay, I got that right. I didn't fully understand the biasing, but I was still able to get the right answer. Okay, let's do 321. Starting with the C code of the form so-and-so, GC generates the following assembly. Fill in the missing expressions in the C code. Okay. C. We'll just go ahead and copy all of this. Oops. I can't type with this book in front of me. Okay. We'll just put an underscore. Wait a minute. Okay. Why is that offset? Okay. All right. So we have some branching here. Every case of this branching is assigning into the return value. So I'd expect the assembly to represent that. And I don't like that they broke this up into multiple lines here, but fortunately our PDF reader here can handle it. So short x and y comes in, we return a short, which is 16 bytes, or sorry, 16 bits, 2 bytes. So it does initial branched base conditional assignment return. So I'm gonna look for RAX. Why is RAX not even used here? They keep on using RBX for the return, which is like not, that's like a mistake. Let me ask AI, maybe it knows. In CS APP, there are some assembly examples that assign into RBX, but I was under the impression, sorry, assign into RBX for their return values, and RAX was used for returns. What is going on here? This as an example. Sorry, I did this. For example, this. I should grab it from here. Thanks for being a piece of shit. Alright, let's take a quick break. I'll be right back. All right, we're filling in the C code here. Move the book over. So let's copy the assembly like we did last time. I hate that I can't copy everything. Okay. Let's grab all this too. Of course, it's going to do out of order. think if I do a column based cut, I think that's when I can do a column based paste. Yeah. And then we had some offsets here that we need to fix up here. And that goes to our, yeah, there you go. That just leaves us with some trailing white space. Okay. So load effective address quad word RSI into RBX. RBX is going to be our temp. They like calling it a temp. RBX is equal to RSI, which is Y plus 12. And then we do a test Q between RDI, test X, and then if X is greater than or equal to, wait a minute, jump greater than or equal to L2. Jump GE. Is that this table over here? No, those conditional moves. Where are my jumps at? Where are my jumps at? I'm gonna actually put some bookmarks in here so that I can easily find these later. Alright, these are my conditional moves. Where my jumps at? There we go. Okay. So the jump here is jump greater than or equal to, which, if we look at the jump condition, is signed XORed with overflow. So overflow is never going to be set, so basically it's signed, so it's not signed. Greater than or equal to 0. Oops, I'm in the wrong page here. Go back over here. Okay. So X is greater than or equal to 0. So that's a good, because RDI is being passed right there. I think that's a good candidate for this. And then RBX is going to be our val. And that's going to be equal to Y plus 12 as our init here. Excuse me. So then we have a move quad word of RDI, which is X into RBX. And then we have some conditional move here. So we're going to do 2 branches here. I'm just spacing this out a little bit. So this is going to be our 2 branches here. So if we move quad word into RDI, which is X, into RBX, so if you val is equal to X, and then I multiply quad word RSI into RBX, so if val is equal to star equal RSI, which is Y, and then this will be a val2 is equal to move quadword RDI, which is X, into RDX. And then this is going to be or quadword RSI, which is Y, RDX, so val 2 or equal Y. And then we're going to do compare quadword RSI and RDI. RSI and RDI are, so it's going to be a comp technically it's that. This would be comp where we do RDI, which is X minus RSI, Y. And then based on that result, we move in RDX. If X minus Y is greater than or equal to 0, which translates to X is greater than or equal to Y, then we move RDX, which was our val2, into val. Okay, so those are things going on there. So that's this thing here. So it's going to be X is greater than or equal to Y. If that's true, then we want val, or we could do less than Y. I think we do the optimistic case first here. So X is less than Y. Then val is going to equal to X times Y. Else, we're going to go to val 2, which is going to be X ORed with Y. And that's all of those. And then last one here. So this was like jump to L2. So this would be less than, actually. So greater than or equal, it jumps down to here. It has to do another test here, though. So let's comment this. This is going to be I divide of RSI and RDI. RSI and RDI have not been touched. So it'd be actually RDI, which is X, divided by RSI, which is Y. And then we're going to do like a compare quadword between 10 and RSI. Compare is a subtraction. So compare RSI, which is Y minus 10. And then if Y minus 10 is greater than or equal to 0, then we move in RDI to RBX. So this could also be done as greater than or equal to 10. Then we do RDI into RBX, which is our return. It's a weird way of doing a return, but this would say basically val is equal to RDI, which we assigned up here. recall RDI is valid too. RDI. Oh no, RDI is X. Fuck, I forgot about that. Alright, we need to fix that then. So this is just saying test XX. X is equal to val, so RBX is val. RDI X is equal to val 2. This is saying do that subtraction, that's fine. This thing, I divide. So this would be X is equal to. Because I divide will assign it to the right hand operand. So X is equal to X divided by Y. Right? So RSI is Y. And then we do the comparison. And then we put RDI, which is gonna be X at this point. Right? Yeah, it's still X. Wait a minute. Conditional move, so RBX is definitely the return. So val is equal to X. But we did the state mutation, okay. Let's go back up here. I want to see what RBX is. Okay, so we checked those two off. Checked all this off. And then basically dealing with L2 here. This looks like it's doing X is equal to X divided by Y. But that wouldn't be in the condition. The condition is only testing Y. So if Y is greater than or equal to 10, that looks to be the condition that they're checking. Then we say val is equal to X divided by Y. And the fact that we blew away RSI in that process doesn't really, or sorry, RDI in that process doesn't really matter. I think that's it. Let's give it a shot. 321. If we go to this problem is similar to problem 318, except that some of the conditions have been implemented by conditional data transfers. Although might seem daunting to fit this code into a framework of the original C code, you will find that it follows the transition rules fairly closely. Okay, so we got a short test val. Short val is y plus 12, got it. X is less than 0, yep. X is less than y, yep. Val is x times y, else val is x or y. Else if y is greater than, I did greater than or equal to, because this is GE. Yeah, it's a GE conditional move. I think that's wrong. If we go back to our conditional moves, yeah, C move GE is greater than or equal to. I think that's greater than or equal to. X divided by y val. Yeah. I mean, this one character is the only difference between what the book says it is. And I think I'm right. Because there's an E here. If that E wasn't there, you could do less than 10. Greater than or equal to 10. Less than You can say 10 is less than y. Just invert the operands. But yeah, okay. I think I'm right, but who knows. All right, onward. We're going to start with the loops now. C provides several looping constructs, namely do, while, and for. No corresponding instruction exists in machine code. Instead, combinations of conditional tests and jumps are used to implement the effects of loops. GC and other compilers generate loop code based on two basic loop patterns. We will study the translation of loops as a progression, starting with do while and then working towards ones with more complex implementations covering both patterns. Do while loops. The general form of a do while statement is as follows: do body statement, while test expression. The effect of the loop is to repeatedly execute body statement. Evaluate test expression and continue loop if the evaluation results is non-zero. If just a body statement is executed at least once. This general form can be translated into conditionals and go-to statements as follows. Loop body statement, t is equal to test expression of t. Yep, go-to loop. I always wondered why do whiles exist in C, because they don't exist in most other languages that I've used, or many other languages that I've used. And I think it's just because it's like the natural first loop you would invent, coming from like an assembly. You just do the thing, and then if you want to loop, test the condition, and then jump back to where the loop started, the body started. That is, on each iteration, the program executes a body statement and then the test expression. If the test succeeds, the program goes back to another iteration. Okay. So we got A, which is C code, and then our go-to version, and then corresponding assembly language. Makes total sense. As an example, figure 319, A shows implementation of routine to compute the factorial of its argument, written n factorial with a do while loop. This function only computes the proper value for n greater than 0. Practice problem 322. I've learned so much, it's the last problem. Alright, we got an A and we got a B. A. Try to calculate 14 factorial with a 32-bit integer. Verify whether the computation of 14 factorial overflows. Okay. What was n factorial? Is 14? Yep, it overflowed. Okay, moving on. The go-to code showed in Figure 319b shows how the loop gets turned into a low-level combination of tests and conditional jumps. Following the initialization of results, the program begins looping. First, it executes a body of the loop, consisting here of updates to variables result and end. It then tests whether n is greater than 1, and if so, it jumps back to the beginning of the loop. Figure 319c shows. The assembly code from which the go-to code was generated, the conditional jump instruction JG, line 7 is a key instruction in implementing a loop. It determines whether to continue iteration or to exit the loop. Reverse engineering assembly code, such as that in Figure 319, requires determining which registers are used for which program values. In this case, the mapping is fairly simple to determine. We know that n will be passed to the function register RDI. We can see that register REX getting initialized to 1, line 1. Recall that although the instruction has EAX as its destination, it will also set the upper 4 bytes of REX to 0. We can see that this register is also updated by multiplication on line 4. Furthermore, since REX is used to return the function value, it's often chosen to hold program values that are returned. We therefore conclude that REX corresponds to the program value result. Reverse engineering loops. A key to understanding how the generated assembly code relates to the original source code is to find a mapping between program values and registers. This task is simple enough for the loop in Figure 319, but it can be much more challenging for more complex programs. The C compiler will often rearrange the computations so that the variables in the C code have no counterpart in machine code, and new values are introduced into the machine code that do not exist in the source code. Moreover, it will often try to minimize register usage by mapping multiple program values into a single register. The process we describe for FactDo works as a general strategy for reverse engineering loops. Look at how the registers are initialized before the loop, updated and tested within the loop, and used after the loop. Each of these provides a clue that can be combined to solve the puzzle. Okay, my mind was wandering while I was trying to read this. That's why I got tongue twisted there. The process we describe for FactDo works as a general strategy for reverse engineering loops. Look at how registers are initialized before the loop, updated and tested within the loop, and used after the loop. Each of these provides a clue that can be combined to solve a puzzle. Be prepared for surprising transformations, some of which are clearly cases where the compiler was able to optimize the code, and others where it is hard to explain why the compiler chose a particular strategy. All right, let's look at that loop again. So we got okay. Pretty simple. So now we're on practice problem 323. 323. For the C code, so-and-so, short DW loop, GC generates the following assembly code. So if we would just look at the loop here, so takes in a short, returns a short, has a temporary y value, which is x divided by 9. That dereferences, or sorry, it obtains a reference to x and stores it in P. And then takes 4 times x and stores it in N. And then goes into this do body where x is increased by y. P is dereferenced and added 5 to it. And since that is pointing to x, basically x gets added 5 to it. And then n gets to subtracted from it. And we do that while n is greater than 0. And then we return x. So basically x is the only value that really matters here. Y is a one-time thing used to then add to x, and P is also just basically the same thing as x. Okay. Which registers are used to hold the program values x, y, and n? How has the compiler eliminated the need for pointer variable P and pointer dereferencing implied by the expression P plus equals 5? Okay, so A, B, so B is just like P is initialized once and never assigned to again. Therefore, it is an alias to its initial value x. And then what was C? C was add annotation assembly code describing the operations program similar to those shown in figure 319C. Okay. Which registers are used to hold program X, Y, and N? X, Y, N. Okay. And then down here, ASM. We'll just copy everything here. Hopefully it'll grab everything in a format that's not too crazy. Okay, it's gonna go crazy. Okay, we'll do that first. This second. ASM. DW loop. And then L2. So everything in between here. Well, RDI and RBX, yep. Looks like these are in line. RDI, RCX. I divide 9. Load effective quad word, that expression. that expression sub q1, yep, test q, oops, and then jump greater than to L2, and then we do the, oh god, that, okay, and we'll just kind of space these like they have in the text. Oh no, that'll be repret. Okay, we're gonna need to space these like that. RBX, so RBX is, X is obviously RDI. RBX is gonna be RCX is gonna be our Y, RCX. RDI also goes into RBX, which is going to be N. And then that means N up here is going to be RBX, probably, tentatively. Here we then say, wait a minute, what is RBX here? RBX is in the loop. This is our, actually, that's not. So here our dx is going to be y is equal to rdi times 4. Yep. X times 4. RDX. And then this thing, I don't know what this is. If I look back at the original code, there is nothing for RBX. Let's see where else is being used. It's being used for RCX, so y plus 5 plus this. Y is not, wait a minute, this is kind of confusing. RCX is y. But then we assign into it here. But we never assign into y. If we look at the test here, test n is greater than or equal to 0. Or sorry, just greater than 0. So our dx is definitely n. Test n if n is greater than 0. Go to .l2. So we have n right. N is definitely this thing. Confirmed. X given. What the fuck is this RCX? RCX and RBX I'm totally confused about. So RBX is being used. RBX and RCX are being added together with 5. And assigned into RCX. It could be that we're just returning RCX because we don't use RAX here, and the calling conventions are crazy town in this assembly. So here we're adding 5 to a value plus another value and assigning into it. So RCX is kind of an X. RBX sub 1 from R here we're doing sub 1 from RDX. RDX is N, we confirmed that. But why is it only sub 1? Should it be sub 2? This code makes no sense, bro. N minus equals 1. So this takes care of X being mutated. So RCX has to be a form of X, right? Our dx is the y that was divided. But we can't mutate that constantly. I mean, I understand that it's treating x and star p as just being the same value. It's adding 5 and y to them each time. I'm going to say RBX and RDI are X. But the thing that weirds me out is that it's loading it into RCX every time. And it can't do that and be correct. No idea. Okay, well, I did what it told me to. So I guess we'll find out how close I am here. This is what, 323? 323. Wait a minute, did I skip over one? Oh, 322. I guess I didn't read the solution here. The computation of 14 bang would overflow 32 int, as we learned in problem 235. When we get the value x while attempting to compute n star, we can test for overflow by computing x divided by n and seeing whether it equals n minus 1 factorial. Assuming that we already ensure that the computation of n minus 1 factorial didn't overflow. In this case, we get so-and-so. As a second test, we can see that any factorial beyond 10 factorial must be a multiple of 100 and therefore have zeros for the last 2 digits. The correct value of 14 factorial is so-and-so. Further, we can build up a table of factorials computed through 14 factorial with data type int as shown below. And 13 and 14 are not valid. Doing the computation with data type long gets us up to 20 factorial, thus the 14 computation does not overflow. Okay, solution to 323. The code generated when compiling loops can be tricky to analyze because the compiler can perform many different optimizations on loop code, and because it can be difficult to match program variables with registers. This particular example demonstrates several places where the assembly code is not just a direct translation of the C code. Although parameter x is passed to the function register RDI, we can see that the register is never referenced once the loop is entered. Instead, we can see that the registers RBX, RCX, RDX are initialized in lines 2 to 5 to x divided by 9, and x and 4 times x. We conclude, therefore, these registers contain the program variables. So it'd be RBX, RCX, and RDX. Yeah, so I was right. You can just delete these comments about the registers. The compiler determines that the pointer p always points to x, and hence the expression star p plus equals 5 simply increments x. It combines this incrementing by 5 with the increment of y via load effective address quad word instruction line 17. The annotated C code is as follows. So yeah, I forgot to fix that part. So that copies x, and then we get y is equal to x divided by 9, compute n. Sorry, this needs to be n. Let's fix that. Then the loop, compute y. Yeah, it's saying y plus equals x plus 5. But that's not what the code does. And then, yeah, this is wrong. There's a lot of shit in this book that is just wrong with the problems. Like this freaking 1 here, it should be a 2. I mean, I'm not criticizing the book, but clearly their editors were not very like careful. I guess this is like an unauthorized edition, but this is the PDF edition, which it's like, when was this thing printed here? So it's the 23rd. It was printed this year. So I mean, clearly they haven't updated this thing, and they don't really get a lot of errata. All right, let's continue on with while loops. The general form of a while statement is as follows: while expression do the body. It differs from a do while in that test expression is evaluated in loop is potentially terminated before the first execution of the body statement. There are a number of ways to translate a while loop into machine code, two of which used in code generation generated by GCC. Both use the same loop structure, as we saw for do while loops, but differ in how to implement the initial test. The first translation method, which we refer to as jump to middle, performs the initial test by performing an unconditional jump to the test at the end of the loop. It can be expressed by the following template for translating from general while loop to go-to code. So it says immediately jump to the test, and then it's basically a do while after that. As example, figure 320A shows an implementation of the factorial function using a while loop. This function correctly computes 0 factorial is equal to 1, the adjacent function. Factorial while jm go-to is a C rendition of the assembly code generated by GCC when optimization is specified with the command line optimization 0g. Comparing the go-to code generated for fact while to that for fact do, we see that they're very similar, except statement go to test before the loop causes the program to first perform the test of n before modifying the values of result or n. The bottom portion of the figure shows the actual assembly code generated. Okay. So you got a practice problem for that. Some more practice problems. And then we get into the for loop. And then we have a switch section on switch statements. That's going to be the big section here. And then we're done with this frickin' section, and I can move on to the next lecture. All right. So let's see how many we got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 pages. I get through that today. I just want to get this section behind me. Feels like I've been stuck in this control section for a long time. Okay, let's see, 324. The C code having the general form loop while short a short b so and so. GC run the command line option OG produces the following code. We can see that the compiler used a jump to middle translation using the jump instruction on line 3 to jump to the test starting with label L2, fill in the missing parts of the C code. Okay, grab this guy here. Okay. Let me just grab all these. So this will be while underscore curly brace underscore semicolon. Oop. Why am I not getting my underscores? There we go. Results is equal to underscore. A is equal to underscore. Term result. Okay. So I want us to reverse engineer this from the assembly. Okay, well, the comparison, so we get RDI and RSI are the two arguments. RDI is being decremented as part of the loop body. So that would be minus or is equal to A minus 1. if we want to follow the actual thing here. So that's this line here. So we're taking RDI and we're subtracting off of 1. RDI is A. Then here we compare, and the comparison is going to be RDI, which is A. Comparison is a subtraction with RSI, which is B. Jump greater than 0. Sorry, 0 here. So the inequality, we can put B over here. So A is greater than B. We're decrementing it. And then we're using REX and EAX appropriately. So result gets assigned 0 initially. And then in the body, we do some math here with RDX. RDX is a temporary variable. Doesn't look like, or temporary register, it doesn't look like it's being used anywhere else. So it's going to be RSI times RDI. So RSI is B times A. Yeah. And we store that in a temporary location. And then we also say, hey, add that onto RAX. So it'd be result plus that. And then we sub. Okay. So that's the reverse engineering of it. Okay, let's check the back of the book. 324. This assembly code is fairly straightforward translation of the loop using the jump to middle method. The full C code is as follows. Yep. It doesn't matter what order we do those in. And then A minus 1. Yep. Cool. Alright, so that's correct. 3.25. The second translation method, which we refer to as guarded do, first transforms a code into a do-while loop by using conditional branch to skip over the loop if the initial test fails. Okay. The second translation method, which is referred to as guarded do, first transforms a code into a do-while loop by using a conditional branch to skip over the loop if the initial test fails. GCC follows this strategy when compiling with higher levels of optimization. For example, with compile line option 01, this method can be expressed by the following template for translating from the general while loop form to a do-while loop. So T is equal to test expression. Then we do the test. If it fails, we go to done. Otherwise, we do a do while. So we just do a little guard up front. Instead of jumping to the test, we just copy that test up. This in turn can be transformed into a go-to code as so-and-so. Using this implementation strategy, the compiler can often optimize the initial test. Oops, I'm on the wrong page here. Boop. The initial test, for example, determining that the test condition will always hold. As an example, figure 321 shows the same C code for the factorial function as figure 320. But demonstrates a compilation that occurs when GC is given command line option 01. Figure 321C shows the actual assembly code generated, while figure 321B renders the assembly code in a more readable C representation. Referring to this go-to code, we see that the loop will be skipped if n is less than or equal to 1 for the initial value of n. Loop itself has the same general structure that is generated for the do-while version of the function. One interesting feature, however, is that the loop test, line 9 of the assembly code, has been changed from n is greater to 1 in the original C code to n is not equal to 1. The compiler has determined that the loop can only be entered when n is greater than 1, and that decrementing n will result in n is greater than 1 or n is equal to 1. Therefore, the test n is not equal to 1 will be equivalent to the test n is less than or equal to 1. Okay. Practice problem 325. For the C code having the general form of so-and-so, GCC run the command with line option 01 produces the following code. I guess it wants us to reverse it, and it just didn't say it. So let's go ahead and do that. All right, let's do some reversing here. So there's initialization in the C code to the result, a conditional test, and then an update to the result, and then an update to B. So A and B are going to be involved here. A is an RDI, B is an RSI. So first thing we do is we test B with itself. So B is less than or equal to 0. Looks like that's what that's doing. Then we jump to the body. Wait a minute, L8. Okay. Did I miss a page here? Oh no, they have extra. It's a weird layout. So they have some extra assembly on the bottom of this page. So L8 would be our move quad word RSI to RAX. RSI is RB. So that'd be return B. And then there's a return in L7 as well. These optimizations, I don't think you're meant to really like do any of this stuff as a human. I don't want to deal with this shit. Okay. Well, this is definitely doing a test on that. If the test fails, then we say, hey, the returned value is going to be RSI. RSI is, of course, B. So that means that B is the value here. So we're just using RSI, and then at the end here, we put RSI into RAX. So that makes sense. So RSI, so B is basically going to be our result. So the fact that we're doing 2 here is kind of questionable. At least we get a copy here. Okay, so that takes care of all of this. Where do we jump to L7? Okay, that's the body of the loop. So this is basically saying, hey, you can just jump to the end. And that makes total sense because RSI doesn't need to be initialized. Okay. All right. Then in here we got the bottom, which is a multiply between RDI, A, and RAX. RAX is currently uninitialized? No. We did a move quad word of RSI into RAX. Okay. So we did that here. We also did that here. So we're basically saying DI, which is A, times the result times A. And then RSI, which you know is to be B, is going to be the subtraction minus A. And then we do our test RSI, which is B. And then we jump here back to L7. Otherwise, we just return. Okay, I think that's it. So if we look 325, while the generated code does not follow the exact pattern of a guarded do translation, you can see that it's equivalent to the following C code. So we have B is greater than 0? How is that even possible? I got less than or equal to 0. Jump less than equal. And then this is, oh, it's jump greater than, sorry. My bad. Jump greater than. The less than equal is like jump if there's no work to be done. If you fail the test, so it's inversion. Okay, and then we do result times A and B minus A and return result. Okay. We will often see cases, especially when compiling with higher levels of optimization, where GC takes some liberties in the exact form of the code it generates while preserving the required functionality. Alrighty, next one. Alright, so in this page has had a bunch of of this stuff again. C an assembly code for while version of factorial using guarded do translation. Let's see, we can see that the compiler used a guarded do translation using the JLE instruction on line 3 to skip over the loop code when the initial test fails, fill in the missing parts of the C code. Oh, this is the instruction here. Note that the control structure in the assembly code does not match what would be obtained by direct translation of the C code according to our translation rules. In particular, it has two different ret instructions. However, you can fill out the missing portions of C code in a way that would be equivalent behavior in the assembly code. All right, 326. Making some progress. Okay. A function test1 has the following overall structure. So we got test1, takes in a short, returns a short, takes in an unsigned short, returns a signed short, and then has the initialization of value, a while loop, and then a return. The GC compiler generates the following assembly code. Reverse engineer the operation of this code and then do the following. Determine what loop translation method was used. Okay. Use assembly code version to fill in the missing parts of the C code. Describe in English what this function computes. Then we get into for loops and switch statements. For loops, switch statements. Switch statements is a little bit interesting. I want to get through this though before I log off. I want to get into the procedures, because procedures are actually interesting. There's less of this like weird optimization stuff that goes on with procedures. I feel like because of the calling convention, the ABI, CABI, like you can't really do a lot without breaking the CABI, you know, the calling conventions. All right, I'm gonna take a little break here. I'll be back in a minute. All right. So what loop translation method was used here? Let's look at the assembly code. So test one, first thing we do is a move long of 1 into EAX. EAX is a return register. Then we jump to L5. So we're doing the method where we jump to the middle, which is called, what do they call it? Yeah, jump to middle translation. We jump to the test immediately. So this is jump to middle. Use the assembly code version to fill in the missing parts of the C code. Okay. Thought I was going to be able to get away with less work here. It's not too much work, but would have preferred to not have to do it. Alright, so obviously this garbage can go, this garbage can go, this garbage can go. This, oops. Here. Oops. Making mistakes all over the place. Alright. I'm just going to put underscores here just to put a placeholder for them. Okay. So we can see the test here is RDI with RDI, and RDI is X. So we say, hey, X, and then we look at greater than, or sorry, not equal. So we say not equal to 0. And then and along 0 with EAX. Return. So jump if it's not equal. So we jump back to L6. So L6 is now our body, which is going to XOR quad word RDI and RAX. this is already there. Okay. Our DI is of course X. So we could say val is equal to X. Or we say, technically we would say val XOR with X. And then shift right quad word. H, I think H is just zero filled. Quad word RDI. And RDI is X itself. So we say X shift right. And because it's unsigned, that's why we don't do this arithmetic shift. 1. And while X is not equal to 0, we XOR it. And at the end here, so say we pass the test, so we don't do the jump. It does an AND with 0. What? Why does it AND with 0? Couldn't it just optimize this whole thing away and just return 0? Because anything ANDed with 0 is going to be 0. But it does it on the lower 32 bits. Not, oh, interesting. It does it on the lower 32 bits, but it leaves the high order 30. That's why. Because the AX is only the lower 32 bits. And all this XORing and shifting and stuff might have left bits in the higher end of the range. So this last part, how do you AND a, so short, wait a minute, we're returning a short, which the short will be only 16 bits. Val and 0. I was thinking maybe they're going to return the high order 32 bits of the RAX register, but that would be if you had a 64-bit value return. This is a 32-bit, or sorry, 16-bit value return. So basically none of this stuff matters. I mean, technically, those bits will still be there, but basically they won't matter. They won't be stored anywhere. They'll get blown away at some point. They're just garbage. Describe an equal what this function computes. It returns 0. I might be wrong on that. It might be something weird. So it moves 1 into EAX. And then say X is already equal to 0. Then it jumps to L5. Passes. It doesn't pass that test. Because it is equal to 0. And then it gets ANDed with 0. I don't see any way around that. You're getting ANDed with 0, which makes it equal to 0. And pretty much anything in this body that's going to XOR and shift X is going to ultimately be ANDed away by this. There will be high order bits in RAX that could potentially be there. And actually, no, those can't be there because this is an unsigned short. So when you XOR, it's still the low. It's only possible because you're shifting right every time that there's only 32 bits that can be affected. So the fact that they're using RAX is kind of misleading because you only need to use EAX. All right, that's my answer. I'm sticking with it. The book might be wrong. The book might be wrong. 326. Where are we at here? Being able to work backwards from assembly code to C is a prime example of reverse engineering. We can see that the code uses jump to the middle translation using the jump instruction line 3. Here's the original source code. Yeah, I guess I could have done that. I could have done a better assignment here. Let me just correct that. I mean, it's semantically the same, but yep. Oh, this is you can just do while x. This code computes the parity of argument x. That is, it returns 1 if there is an odd number of ones in x, and 0 if there is an even number. We'll ask AI just to double check. In CS APP, this function comes up. What does it compute? Yeah. Yeah. The book's on crack. The book is on crack. All right. For loops. So we got for loops and we got switches. And then we're done with this. Moving on to procedures. Okay, for loops. The general form of a for loop is as follows. For, init, test expression, update expression, body statement. The C language standard states, with one exception, highlighted in problem 329, that the behavior of such loop is identical to the following code using a while loop. It's identical, but I think my understanding is that you can also declare a variable inside the while init expression, in which case it's scoped to that block. At least that's the way it behaves in like Go. The program first evaluates the initialization expression in init expr. It enters a loop where it first evaluates the test condition test expression. Exiting, if it test fails, then executes the body of the loop body statement, and finally evaluates update expression. The code generated by GCC for a for loop then follows one of our two translation strategies for while loops, depending on the optimization level. That is, the jump to middle strategy yields go-to code, while the guarded do strategy yields so-and-so. As examples, consider the function, a factorial function written as a for loop. So we got long I and result is equal to 1. And then we say I is equal to 2, I is less than. Why? I guess this is before they could declare. Can you declare? I think you can declare. Vim, I'll just say test decal. I'll say for decal.c. Main for int I is equal to 1. I is less than, 10. I plus plus, or a lot of people like this plus plus I. And then we'll just say printf %d new line I pound include standard in standard io.h. We need standard lib. There we go. Looks like it's valid. Make, build, test, decal. Test for decal. It works. Oops, that's not what I wanted. Vim test for decal. Yeah, it works as expected. And I'm not using any fancy, I guess I am using C23 to build this. If I use standard, let's see, 89, make, yeah, before C99, 99, make, build, for decal, yeah, sorry, make, clean, make, just make sure we got it, yeah, okay. Let's go back to 23 here. So that's why they do it this way, because they want C89, C90 standard support, I guess. Alright, so then we go in our loop, and we just multiply our result times I. As shown, the natural way of writing a factorial function with a for loop is to multiply factors from 2 up to n. And so this function is quite different from the code we showed using either a while or a do while loop. We can identify the different components of, it's odd that they did that though, because this book was authored in like what, 2016? It's like, I think we can assume C99 in 2016. Yeah. I don't know. We can identify different components of the for loop with the code as follows: init, test, update, body. Substituting these components into a template we have shown to transform a for loop into a while loop yields the following. It's a fact for while. Yep. Applying the jump to middle transformation to the while loop then yields the following code. Indeed, a close examination of assembly code produced by GCC within command line option OG closely follows this template. Practice problem 327. Let's go ahead and kill that. Jump down here, 3.27 dot. Okay, what we got going on here? Write go-to code for a function called Fibonacci. So this is going to be C. Fib void int n. Write a go-to function for print Actually, I'll just pull this out here. Wait, 327. Oops. Clearly not, right? I thought you started off with 0, 1. Let's get the sequence here. So you start with 0, 1, and then you add those two together, you get 1. You add those two together, you get 2. You add those two together, you get 3, 5. So I think this is wrong. Start with 0 and 1. And then A being equal to B would be right. So this would be 0, 1 initially. And then A would become 1 and B would be equal to 2, which is wrong. I think we need a temporary variable here. Been a while since I did this. Okay, let's try doing this now. So 0, 1. Temp is equal to A, which is 0. A is equal to B, which is 1. B plus equal to temp is going to be 1. Alright, next go around. You get temp is equal to 1. A is equal to 1 again. B is going to be equal to 1 plus temp, which is 1, which is 2. Okay, so I think I needed that temporary variable there. I think that's right. Two, 3, 5, 8, 13, 21, 34, 55, 89, 144, 1, 2, 2, 2, 3, 3, 3, 7, 7, 6, 10. Okay, that looks right. Looks right. Okay. Okay, and then I wanted to just do what? Write goto code for the function called Fibonacci to print Fibonacci numbers using a while loop. Wait a minute, I thought we were using goto code. You're talking about while loops. Let's see what the general form is that they use. This is like problem 27. They did not use a while loop. They used straight up gotos. Okay. We could change this to be a decrement, right? That saves us one variable there. Oops. Looks like there's some errors. Less than 0, greater than 0, which means not equal to 0. We'll not deal with negative numbers. Alright, still works. Okay, let's translate it to go-to code. So we say if loop go to loop, otherwise we done. Test okay. Init. Which version did he want? He wanted a specific version, right? While loop, apply guarded do transformation. So this is the guard, and then this is the do, and this is the while. And we can eliminate this and just fall off the end here, right? Just do like a return. Can I do that? No. I have to have assembly. I have to have assembly like situation here. Okay, I'm pretty happy with that. Let's go ahead, write that out, make it, run it, and then we'll read it in here. Read it. Test 227, I think it is. Shit. Chapter 03. Test 227. See. Maybe we can delete all that. Delete all this too. Okay. I'm not unhappy with that. 327. See what they had over here. This exercise is intended to reinforce your understanding of how loops are implemented. To use logs. He said print. So it was his mistake. It says right here, call Fibonacci to print Fibonacci numbers using a while loop. So his implementation is already incorrect. But, so he has next, first, second. And I is equal to 2. If n is less than or equal to 1, go to done. Otherwise it goes into a loop where next is first and second added together. First is now second, second is next. I plus plus, if I is less than or equal to n, go to loop. That's one way of doing it. I like mine better. All right. We see from this presentation that all three forms of loops in C, do while, and for, can be translated by a simple strategy generating code that contains one or more conditional branches. Conditional transfer of control provides the basic mechanism for translating loops into machine code. So now we got another problem here, 2 problems, and then we start on switches. Jobs, okay. Vim problems, 3.28. Okay. This one, a function test2 has the following overall structure. The GCC compiler generates the following assembly code. Reverse engineer the operation of this code, then do the following. Use assembly code version to fill in the missing parts of C code. Explain why there's neither initial test before the loop nor initial jump to the test portion of the loop. Describe in English what the function computes. It's going to be an ABC type deal. So we're going to have C, and we're going to have some assembly. So just put them all in here. Grab all this stuff here. Beautiful copy paste action. That did not work out right. There we go. And grab all this stuff here. Really do wish that this was a little bit nicer to copy. Okay. Oops. Oops. There we go. All right, so EDX V1 is equal to 1. If we look for where RDI is being used, it's being used here and here, so it's going to be involving X for something. And then EAX, we'll say return 65. ECX, we'll say V2 is equal to X. RCX, and with 1, V2 so if you AND with 1, you're basically converting it to a Boolean value, but it's only on the ECX bits, the lower 32 bits, and it's an unsigned, which makes it a unsigned would be what's the unsigned test? What does that mean? It's actually short. Short. Fix their shit here. Test 2. Unsigned short X. Because it's a short, that means it's only 16 bits, which means that we don't have to consider any of the weirdness around higher order bits. If we AND 1, like the literal value 1 with ECX, which is the same thing as RCX, we're basically converting it into a value like that. And then here, RAX and RAX. So we set EAX up here to the ret. So ret here is going to be equal to, wait a minute, ANDing with yourself? That's a no op. Is that right? Did they just throw like a no op in there for no reason? Oh, it's add. I thought it was and. Let's say times equals 2. Or quad word. I think it's because I was looking at the or and I just read that as and it's all said and up here. I didn't see the add. Okay, add. All right, so we got OR, RCX, and RAX. So RAX is the return. And we're saying we're going to OR you with RCX, which is V2. OR to V2. And then we're going to shift right quad word RDI, one bit. RDI is X. It's being right shifted by 1. And then we add quad word 1 to RDX. RDX now is EDX, which is V1, plus equals 1. And then we say jump not equal to Okay, I gotta go back to my table here. So many tables. Okay, and is it and or add? It's add. Add definitely has an effect. Although all arithmetic and logical operators set the condition codes, the descriptions of the different set instructions that apply, yeah, blah, blah. Wait, I'm on 28 here. Yeah. If V1 is not equal to 0, if V1 go to L10, okay. So you got a V1 and a V2. EAX is return. So val is going to be our EAX. So we say it's a val. They only have 2 variables here, and I have 3. So we have val, and we have edx, which is V1, which is set to 1. I'm guessing V1 is I. So what the frick is this V2 thing? So it's gonna be I. If I is equal to 0. So we're adding, we start at 1, and every time we go through, we add 1 to I. And then we say if I is not equal to 0. Well, you're just going to iterate up to infinity then, or until you wrap around. I don't see any comparisons with x or anything. Oh, maybe v2 is x. It's like a copy of x. I mean, every loop it initializes it. It's something declared inside the loop. Because every loop iteration it reassigns it. We call it temp. Temp. So it takes care of that. I don't understand this last condition here, this jump. I'm going to ask AI about this because I just don't understand it. Oh, so it's not equal, which means that the zero flag would be set to 0. So you're not saying not equal to 0. You're saying effectively I is equal to 0? No. Not equal to 0. I'm confused. This is the way I originally interpreted it is I is not equal to 0, starts at 1, and it's going up to infinity. Did I miss an instruction somewhere? Nope. Yeah, it seems like a while true. All right, let's finish this thing up. So use assembly code version fill in missing parts of C code. We did that. Explain why there are is neither an initial test before the loop nor an initial jump to the test portion of the loop. The initial loop can be assumed to be true. to always be true. C, describe in English what the functions compute. What the fuck? I have no clue. Oops. All right. 328. This problem is trickier than 326 since our code within the loop is more complex and the overall operation is less familiar. Here's the original C code. I is equal to 65. The fuck? It's adding 1 though. How is that possible? Sorry, it's meant to be times, not plus. All right, 329. Executing a continue statement in C caused the program to jump to the end of the current loop iteration. The stated rule for translating a for loop into a while loop needs some refinement when dealing with continue statements. For example, consider the following code. If I and 1 continue. Example of for loop containing a continue statement. Some even numbers between 0 and 9. What? I just want to get this stuff done, man. What would we get if we naively applied our rule for translating the for into a while loop? What would be wrong with this code? We need to make sure that the increment of I always happens even with the continue. We wouldn't be able to just jump to the start. To go to, where does it jump? Jump to the start, the loop. B, how would you replace the continue statement with a go-to statement to ensure that the while loop correctly duplicates the behavior of the for loop? 329. Our standard rule for translating for loop into a while loop is just a bit too simplistic. This is the only aspect that requires special consideration. Applying our translation rule would yield the following code. This code is an infinite loop since the continue statement would prevent the index variable I from being updated. The general solution is to replace the continue statement with a go-to statement that skips the rest of the loop body and goes directly to the updated portion. That's what I said first. Okay. 330. Switch statements. Last statement. This one's actually kind of interesting with the jump table. All right. Boom, 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 boom. A switch statement provides a multi-way branching capability based on the value of an integer index. They are primarily useful when dealing with tests where there can be a large number of possible outcomes. Not only do they make the C code more readable, but they also, oops, I'm on the wrong page here, sorry about that. But they also allow an efficient implementation using a data structure called a jump table. A jump table is an array where entry I is the address of a code segment implementing the action the program should take when the switch index equals I. The code performs an array reference into the jump table using the switch index to determine the target for a jump instruction. The advantage of using a jump table over a long sequence of if-else statements is that the time taken to perform the switch is independent of the number of switch cases. GCC selects a method of translating a switch statement based on the number of cases and the sparsity of the case values. Jump tables are used when there are a number of cases, e.g. 4 or more, and they span a small range of values. Figure 3.22a shows an example of a C switch statement. This example has a number of interesting features. Let's take a look at it. Oh, this is the one that they had in the presentation. Let's go back. Including case labels that do not span a contiguous range. There are no labels for cases 101 and 105, cases with multiple labels, cases 104 and 106, and cases that fall through to other cases, because the code for the case does not end with a break statement. Figure 3.23 shows the assembly code generated when compiling switch EG. The behavior of this code is shown in C as the procedure switch EG impl in figure 32b, or 322b. The code makes use of support provided by GCC for jump tables, an extension to the single. What? The code makes use of support provided by GCC for jump tables, and an extension to the C language. So they were able to make C code out of it. Interesting. As an extent, the array JT contains several entries, each of which is an address to a block of code. So if you go back over to the code, it's kind of hard to see when you're reading text here. So they initialize a jump table here. So the jump table is a static. Basically it's a void star, a pointer to something, and it has 7 elements, which I think you can leave the 7 off because compiler can compute that for you. But then we have A, def, B, C, D, def, that's default, D, A, D, default, B, C, D, default. Okay. So these are all the values of the jump table. And we say, hey, the ampersand is a reference to location A, location B. I think that's some special syntax. They're just saying pointers to wherever this places in memory. This code places in memory. Let's see here. N minus 100. Oh, so we're switching on N. Val is just equal to X. Val is then mutated and assigned into the destination here. So we subtract off 100 because our first case, or lowest value case is 100. So we just subtract off 100 so that 0 is this case here, location A. So that index, if index is greater than 6, then we just go to our default. Otherwise, we go to our jump table value, which is one of these. If it has a break, then we go to done. If it doesn't have a break, it just falls through. And yeah, pretty simple. Okay, let's go back to here. These locations are defined by labels in the code and indicated in the entries in JT by code pointers consisting of the labels prefixed by ampersand. Recall that the operator ampersand creates a pointer to a data value. In making this extension, the authors of GCC created a new operator, ampersand, to create a pointer to a code location. We recommend that you study the C procedure switch EG-impl and how it relates to assembly code version. Our original C code has cases for values 100, 102 to 104, and 106, but the switch variable n can be an arbitrary integer. The compiler first shifts the range to between 0 and 6 by subtracting 100 from n, creating a new program variable that we call index in our C version. It further simplifies the branching possibilities by treating index as an unsigned value, making use of the fact that the negative numbers in a 2's complement representation map to large positive numbers in an unsigned representation. You can therefore test whether index is outside of the range 0 to 6 by testing whether it is greater than 6. In the C and assembly code, there are 5 distinct locations to jump to based on the value of index. These are location A, B, C, D, and default, where the latter is the destination for the default case. Each of these labels identifies a block of code implementing one of these case branches. In both the C and the assembly code, the program compares index to 6 and jumps to the code for the default case if it is greater. The key step in executing a switch statement is to access the code location through the jump table. This occurs in line 16 of C code with a goto statement that references jump table JT. The computed goto is stored by GC as an extension to the C language. The computed goto is supported by GC C as an extension to the C language. In our assembly code version, a similar operation occurs on line 5, where the jump instruction operand is prefixed with star, indicating an indirect jump, and the operand specifies a memory location index by register EAX, which holds the value of index. We will see in section 3.8 how array references are translated into machine code. Our C code declares the jump table as an array of 7 elements, each of which is a pointer to a code location. These elements span values 0 to 6 of index corresponding to values 100 to 106 of n. Observe that the jump table handles duplicate cases by simply having the same code label for entries 4 and 6, and it handles missing cases by using the label of the default case as entries 1 and 5. In the assembly code, the jump table is indicated by the following declarations to which we have added comments. So let's look at the assembly for the switch. All right, looks pretty reasonable. These declarations state that within the segment of the object code file RO data, for read-only data, there should be a sequence of 7 quad 8-byte words where the value of each word is given by the instruction address associated with the indicated assembly code labels. L3. Label L4 marks the start of this allocation. The address associated with this label serves as the base for the indirect jump. Line 5. The different code blocks C labels location A through location D, implement the different branches of the switch statement. Most of them simply compute a value for val and then go to the end of the function. Similarly, the assembly code blocks compute a value for register RDI and jump to the portion indicated by label L2 at the end of the function. Only the code for case labeled 102 does not follow this pattern. To account for the way that the code for this case falls through to the block of the label 103 in the original C code, this is handled in the assembly code block starting with label L5 by omitting the jump instruction at the end of the block, so that the code continues executing in the next block. Similarly, the C version switch eng impl has no goto statement at the end of the block starting with label block B. Examining all this code requires careful study, but the key point is to see that the user jump table allows a very efficient way to implement a multi-way branch. In our case, the program could branch to 5 distinct locations within a single jump table reference. Even if we had a switch statement with hundreds of cases, they could be handled by a single jump table access. All right, we got some practice problems, and then we're in procedures. Damn. We're almost there. Might actually take a break at procedures just to get some dinner, and then I'll come back. Well, it's almost 6. I want to get to bed by 8. I might just sign off. Yeah. Because I want to start getting to bed extra early. Practice problem 330. In the C function that follows, we have omitted the body of the switch statement. In the C code, the case labels did not span a contiguous range. In some cases had multiple labels. In compiling the function, GC generates assembly code that follows for the initial part of the procedure with a variable x and RDI. It generates the following code for the jump table. Based on this information, answer the following questions. A and B. What were the values of the case labels of switch statements? What cases had multiple labels in the C code? Okay. Well, we had these values in the jump table. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Nine different values in the jump table. And then if we go back here, so RDI is our X. We add 2 to X. So we offset it by 2. And then we compare RDI with 8. And then jump if it's above to L2. So L2 is our default. Otherwise, we jump to L4, which is not even in the cases. It's probably our start of the jump table. Yeah, okay, that makes sense. The value of RDI times 8, because it's going to be Yeah, that makes sense. Yep. So we add the value of the memory address of L4 to RDI times 8. So that times 8 turns that zero base index into one that's sized for a pointer, and then adds offset. Okay. What were the values? What were the values of the case labels in the switch statement? So it's gonna be +2 on all these. So this will be 2, 3, 4, 5, not there, 6, 7, and 9. L5, so 3 and 9 were together. So 8 and 2, 3, 4, 5, 6, 7, 8, 9, and 10. Six and 9 were missing. These two were together. These two are together. So the values were 2, 3, 4, 5, 7, 8, and 10. B. So this is what were the values of the case labels switch statement. What case had multiple labels in the C code? What cases have multiple labels? Okay, I can see what they're saying there. So that would be 5 and 7, and 3 and 10. Okay, let's go back to the answer key. This is going to be, what do we got here? 330. Right? Yeah, 330. This problem gives you a chance to reason about the control flow of switch statements. Answering the question requires you to combine information in several places. Assembly code. Wait a minute. There's C? There is no C on that. Man, these editors, they did not do a good job with this. It says problem, solution page 374, 272, yeah, and there's only A and B printed. But there's a C in the answer. Okay. Well, the case label is switch statement. Oh, because it added to. Shit. I fucked that up. Which means that this is subtract 4. So it'd be -2, -1, 0, 1, 3, 4, 6. This would be 1, 3, -1. Huh? Yeah, -1. and 6. Okay. So -2, -1, 0, 3, 4, and 6. What about 1? 1 would be 3. They forgot 1 there. And then they have case with destination L5 has labels -1 and 6. Yeah, 1 and 3. -2, -1, 0, 1, 3, 4, and 6. 1, 2, 3, 4, 5, 6, 7. Okay, I got them right. 3, 31. I added 2 instead of subtracting 2 like an idiot. Alright, for C function switcher with the general structure. So we have a switch with a bunch of stuff in it. GC generates assembly code and jump table. Oops. GC generates assembly code and jump table shown in figure 324. Fill in the missing parts of C code except for the ordering of the case labels C and D. There's only one way to fit the desired cases into the template. Alright, this is the last problem. And then I am getting off for dinner. Oh shit. Alrighty. Fucked up this page here. I'll fix that later. Alright, I really don't want to do this one. I've done so many of these. Kind of boring. Case underscore case A C is equal to underscore fall through. Okay, case underscore, come on, that's case B, val is equal to underscore and break. Case underscore case C and case underscore case D both share the same body here, val underscore break. Case underscore, oops, case E, val underscore, oops, break. Default val underscore destination val. Okay. Now we look at the assembly code and reverse engineer it. So it's basically the case values and then what we're actually doing when we're assigning things to it. So the big kind of tell here is that the two underscores here, the two cases that are next to each other are identical. They'll have identical entries here. So 3, 2, 5, 2. So 2 and 2. Oh, there's 3? What? So 2 is default. Let's go ahead and decode the jump table here. So if I can copy correctly, cell 2 is going to be default. L3, 5, 6, 7, 5, 5. So case C or D, and then 3, 6, and 7 we'll have to figure out here. Long A. Okay, the first thing we do is say, hey, compare quad words 7 and RDI. RDI is B. Do we even use B? Nope. It is not used in the switch body or switch condition there. We're switching on A. But we compare 7 to B. And if it's above that value, then we jump to L2. And L2 is default. So why is RDI being treated that way if we're switching on A? That doesn't make sense. Does not make sense. I think they meant to say RSI there. And then we do a jump through L4. That makes sense. RDI times 8. That makes sense. So I think RDI, because we're not modifying it, we just use it raw. I think it's anything above 7. So it'd be 0, 1, 2, 3, 4, 5, 6, 7. Yeah, that makes sense. So this is going to be value 0, 1, 2, 3, 4, 5, 6, 7. So the default, let's go ahead and figure out the default case. That'd be easy. That's L2. So we're moving RSI into RDI. RSI is A. Why is there a section read-only data here? Interesting. I mean, shouldn't it all be read-only? No. All right. So that's a default. Default was L2, RSI into RDI. So B is going to be the value. I think the switch needs to be on B too. But it seems like B is going to be the value that gets... Oh no. Destination is RCX, yeah. RDI is basically val. RDI is val. RDI is val. And I think they switched on A incorrectly. I think it should have been switched on B. All right, what else can we tell from this? So C and D we can tell. So L5 is going to be C and D here. And C and D are easy. So they're 2 and 7. And they're doing a addition between RDX and RSI, which is C plus A. C plus A And then they're also doing a shift arithmetic left, so they're multiplying by 2 times 2. And then we can do it like that. Then jump to 6. So 6 would be the end. Yep, that's correct. So L7 is the thing that falls through. So it's going to be L7 is the fall through. No, is case A. So L7 would be case A, which is 5. Because that has the fall, it's missing the jump. And so what that does, it does an XOR of 15 with RSI. RSI is A. So 15 XOR'd with RSI, which is A. And then RSI is then moved into RDX, which is C. Okay. And then here, I don't know why we need C. Maybe C is in case B somewhere. So this is going to be L3 is case B. Case B. So this is going to be 0. Case B L3, we're going to say 112 plus RDX, which is going to be our C. 112 plus C, and then move that into RDI, and then jump. Okay. Oh. RDI is also B. Oh no. Fuck. RDX. Oh, C was an argument. Okay, I was wondering about that. Okay. So here we say add 15 to RSI A and store it into C. And then we just see here. Okay. So those are filled out. I think that's everything except for case E, which we only have one left here. So it has to be this guy. So that'd be case 4. And the value for L6. Wait a minute. Huh? L6, I thought was the default was L2. L6 was just like val. I think that's how you do it, because for case E, L6, it's jumping to L6 directly, which means that it's a no op. So if there's a val there, it has to be val. Val is equal to val. I don't think I have all of these right, but we'll see. We'll see how many I got right. Let me put my pen over here. All right, 331. The key to reverse engineering compiled switch statements is to combine the information from the assembly code and the jump table to sort out the different cases. We can see from the JA instruction that the code for the default case has label 2. We can see that the only other repeated label in the jump table is L5, and so this must be the code for cases C and D. Got that. We can see that the code falls through at lines 8, and so L7 must be case A. Yep. And label L3 must be case B. Yep. That leaves only L6 to match case E. Yep. The original C code is following: log out switch A 5, C, which is B. Wait a minute. Looking at the assembly. The assembly for case 5, which is, case A, which is L7. XOR with RSI. RSI is clearly A. So because they got RSI, yeah, they're crazy here. All right, and then we got 112 plus C is equal to val. Yep. 27 val is equal to C plus A. They did left shift 2. I just did times. Wait a minute. Was it left shift 2? Okay. I was going to do times 4, which is equivalent. Case 4 val is equal to A. That makes more sense, because that would have been the default too. It's really disappointing how many errors there are in the book. All right, that is it for this session. That was a 3-hour and 18-minute session. I've concluded all the way up to procedures, which is the next lecture. And I'm going to really enjoy this section on procedures. I think it's really important to understand at deep level procedures. So now that I'm done with that, I'm going to go over to README. And I'm going to mark off my control. And I look forward to jumping into the procedures next. I think what I might do is, just add everything here. I might just eat dinner and watch the lecture on procedures just off stream here while I wind down for the evening. Okay. Okay. Oh, we got a little white space there. 323. On A. Oops. No, I was on C. C? Yeah, C. Come on. All right. Let's page through, make sure we don't have any weird things. Okay, get CIM, oops, get LGA 3, get CIM, and we'll say progress on chapter 3, get push all. Cool. And I am starving, so I'm gonna go get dinner, and I will watch the lecture off stream for procedures. And I think what I'm gonna do moving forward with these lectures is because I'm tempted to watch the lectures during my downtime. So I think what I'm gonna do is just watch the lectures once before I start the material in the book, and then maybe once or twice while I'm reading to kind of fill in some of the gaps in understanding when I'm reading. But I'm not going to jump ahead. I'm not going to watch lectures for material that I'm not working on, basically. So now that we've hit the procedures section, I'm going to watch that lecture. Cool. All right. I will be on tomorrow for procedures.